Good afternoon, and welcome to the IMS Sustainment keynote and panel discussion. As the Executive Secretary mentioned yesterday, we are closing in on 30 years since the signature or the signing of the treaty. And so, of course, some of our stations are almost that age as well. So the PTS has been actively working on a strategy on how we can continue to sustain the IMS for at least 20, preferably 30 years and into the future. So during this S&T, we've had a few sessions, as you would have noticed from the program. We've had an oral session that was yesterday. We have a poster session tomorrow. And then, of course, we have this keynote and panel session for today. Now, the main aim of all these different sessions is not only to share the results that we have had or through all our work, not only to share those results with you, but also, of course, to learn from you, to interact with yourselves, and to learn from how we can improve going forward and how perhaps different networks also sustain their equipment and their stations. So with this in mind, I would like to introduce our keynote speaker. She is the director of the IMS division, Ch1 Perez Campos, and she will present a keynote entitled Sustainment of the International Monitoring System, the Value Beyond the Strategy. Please welcome Ch1.
Good afternoon. It's my pleasure to be here with you this session. And I'm going to talk about the IMS sustainment. But I want to share something more about the strategy that we have been developing and following, because the network has so much to give. There's so much value in its data, so I want to highlight that part. So there's an before and after the treaty was open for signature. Before, more than 2,000 tests took place in our world, in more than 60 places. After 1996, when the treaty was open for signature, only about 10 tests have taken place in a couple of places. And since the international monitoring system was established, we have been able to detect the 6 tests that have taken place in only one place, in only one site. So the international monitoring system is one of the pillars of the verification regime. Its objective is to collect, analyze, and store and distribute data. So for that, 337 facilities are supposed to be installed around the world. They are integrated in 4 technologies. The first one is the seismic technology, where we have 50 primary seismic stations and 120 auxiliary seismic stations. We have the infrasound technology, with 60 stations, and we have the hydroacoustic technology with 11 stations. Those 3 networks allow us to listen to anything that is happening underground, on the surface, or underwater. Then, to be able to say if it was a nuclear test, we have the radionuclide technology. With that, we can sniff what is happening and discriminate from a regular explosion or a nuclear test. Today, we have 307 facilities certified in the network. That put us in about 92% of the network. Here in this graph, you can see the history of the installation and certification of the network. Each bar corresponds to the number of stations that have been certified per year. So the graph goes from 2000 on your left to 2025 on your right. The small green bar at the very right is the infrasound station IES-16 that was certified just last month, located in China. Please note the shape of the graph. You have a high peak around 2005, and then we have a decline in the number of certifications with time. Once you install and certify a station, then you move it to operations. And in operations, you need to take care of the daily activity in the station. Make sure that it's working properly and delivering good quality data. For that, you might perform preventive maintenance or corrective maintenance if needed. You need to make sure that you have enough spare parts to act quickly in case you have a failure and reduce the time that you have between the failure and coming and sending data again to the international data center. Then the station will get older, and then you will see more failures in the station. And for that, you might need to plan some equipment replenishment or replacement. Eventually, your station is going to be old, having lots of problems, and then you need to recapitalize most of that station. And when that happens, you are starting a new cycle for the life of the station. Here are some examples of activities that take place at the different stations for the maintenance and operations. So you can see in the images, for example, a maintenance for the underwater systems, for the hydroacoustic stations in the center top, where divers go and check the health of the cables for the hydroacoustic stations. Also in the center bottom, you can see maintenance being performed in a radionuclide station. And then on the left top, you can see an upgrading or updating of infrasound equipment in infrasound station. And then in the other three panels, you can see some actions in seismic stations, checking the digitizers or installing seismometers. So remember these green bars that we saw at the beginning, where this bell shape center on the left shifted to the left. So that was, again, the number of stations certified with time. So as I mentioned, the stations start getting older, and then you need to recapitalize the station. That means changing the old equipment for new equipment. And when you do that, you need to revalidate the station that is still performing at the level that we need at the IMS. And when that revalidation takes place, then you see a red bar here. So that revalidation can be used as a proxy of these recapitalization actions that we conduct. If you only focus on the green bars, you will expect to have a similar shape in the future because you have the network becoming old, so you need to replenish the stations again to go to the second cycle of the network, and then you will expect to have a similar shape in the future. So where are we now? Are we starting to see that new shape, but we are spraying over time? And then does that mean that we are delayed on having this recapitalization of the stations? Or where are we and where we are going? Do we expect to have a similar shape, or how we're going to handle in the future? Having a similar shape means lots of money very close in time. So that's not affordable. We need to come up with a different solution, something that allows us to spread that financial needs over time. So What is the current status of the different elements and equipment in the station if we are delaying that recapitalization or that new cycle of the network? In the plot on the right, what you can see is the distribution of the age of the digitizers installed in the seismic stations, the infrasound stations, and the T-phase stations of the hydroacoustic network. So on the x-axis, each bar corresponds to a 2-year period, while the vertical axis corresponds to the number of digitizers with that bracket of age. You can see a red vertical line. That one is set at 10 years. 10 years old for the digitizers correspond to the expected life span of that digitizer. So if we consider that younger than 10 years, that means the bars on the left, they are younger than the life expectancy of our digitizers. Any bar on the right corresponds to all digitizers in the network. So this is a very striking figure telling us that the digitizers in the IMS network are old. That's the key message here. So what do we want to do for the future is to shift that shape, that distribution to the right of the red line, right? You want to have young digitizers that are performing well and giving you good quality data. So if you compare a digitizer with something more daily basis, like your cell phone, well, cell phones now have a very short lifespan, right? You want to change them like every 3 years, probably, because then you cannot use apps, their batteries are failing, you keep bringing them to the shop to, the little hole for the connector is failing every time, and so on. So you're spending lots of money on fixing those problems on your phones. That is the same thing for a digitizer. There will be some time that you are going to be spending too much money into repairs of that equipment, so you better change it. And that is close to those 10 years. Anything older than that, you are going to start having lots of problems with that. And it's not only about the money, it's about the data. Because every time that you have a failure in your equipment, you are losing data. So what we have currently at the network is a technical debt. This technical debt comes from 3 different factors at least. One of them is that we have deferred some of the IMS sustainment activities needed at the network. This could be a result of budgetary resource constraints. The other important element that we need to consider is the obsolescence of the equipment. Digitizers have becoming obsolete. We are operating some models of digitizers that are obsolete, and they are not produced or maintained anymore by the manufacturers. So this, remember the graph on the right, we're talking about digitizers that are over 20 years old. So this is really old in terms of digitizers. Some of them are already obsolete. So if they fail, there's nothing we can do to repair them anymore. So with this in mind, we were tasked since many years ago, let's put ourselves in by the end of 2022, with the task of developing a sustainment strategy for the network. The objective of this strategy was to protect the network. There has been a significant investment from the states to install this network and to operate it. We should not lose this investment. But again, it's not only about the money, it's about the data. We need to have good data availability and good data quality. And for that, we need a good performance on the instruments. So we have been developing a sustainment strategy for the long-term sustainment of the network. There's a very important fact about this network. It's a finite number of stations. Not like other networks that keep growing with time. The IMS network has a specific number, and it's established by the treaty. So currently, we are over 90% of the stations established. When we started the development of the strategy, it was 90%. The other important thing is that because of this finiteness of the network, we can transition from focusing on the installation to focusing on the sustainment of the network. And that is very important that some other networks cannot do because they keep installing and installing more equipment. The other thing important is that because it's now a mature network, we can transition from reactive sustainment to proactive sustainment. How to do that, right? So when we are looking for the different elements of how to decide to recapitalize a station or to change an equipment or to update something in the station, we took different elements. And we can see them all collected here. So we need to look into the supply chain practices. We need to look in failure analysis studies for the whole network, and so on. But it's very important to realize and to recognize that all this sustainment strategy for the network is based and supported by people. And by people not only at the PTS, all the engineers that work on maintaining and operating the network, but also by station operators, who are the first front of identifying problems with the stations, looking for the first level of solutions, and then reaching out to the PTS staff to come up with better solutions or engineering solutions. But also, if we're looking into the future, we're going to be looking for ways to do this more effectively, talking about money, but also about technical aspects. And for that, we need to keep an eye on the technology. So we heard this morning about AI and the introduction of AI in monitoring the health of the stations. This is something that we need to incorporate in our way that we sustain the network and analyze the data. So we need to keep an eye on technology foresight. So this also will be a big pillar when we are carrying out our activities for sustainment of the network. So how we develop this strategy? First, we look at the different elements that each technology has at the stations. So it's recognized that each station is subdivided in subsystems. We identify the critical subsystems. For example, for the seismic stations, we say critical subsystem is a seismometer, it's the digitizer, and it's the computer that authenticates the data, right? So those are the critical subsystems. So we need to check for these subsystems a comprehensive estimate of the lifespan of each of these subsystems. And for that, we consulted manufacturers. We consulted the obsolescence of each of these subsystems. We consulted technology foresight, how the developments of the new digitizers, for example, is going. We reach out to station operators to several surveys to understand also their perspective and experiences on these subsystems. We check on our capability and the capability of the manufacturers to repair the equipment. And also we balance between maintenance of the equipment, repairment of the equipment, or actual replacement. And then we came up with the distributions that you can see on the right. Those graphs correspond to the 4 major networks. So you have the seismic on top left, the hydroacoustic on the hydroacoustic hydrophone segment on the top right, then the infrasound on the bottom left, and the radionuclide on the bottom right. And now you can start seeing that bell shape that we saw in the installation phase, on the installation distribution. It is very clear in the seismic stations. You can see a peak now of the needs of the number of subsystems. So the bars correspond to number of subsystems needed per biennium. And the different colors in the bar corresponds to the different subsystems in the network. So you can see that bell shape already for the seismic, and then you have a decrease in the number of subsystems that you will need, and then again an increase. And that is the natural cycle of the network. You slightly see a similar pattern on the infrasound, but because of the infrasound stations are younger, you don't see the high peak now, but you will see it later in this 20-year period. With the radionuclide, it's not that clear, and it's not because the radionuclide faces obsolescence of the equipment more rapidly. So we have distributed over time to roll out the new generation of subsystems there. So anyway, now we have this distribution of needs over 20 years. Why 20 years? Some people say like it's too much. Some people say it's not enough. Let's first think about something very important. We're talking about a network that we like to preserve for eternity. I'm sorry, I'm a seismologist, and I like to think that seismic networks are going to stay forever. So let's focus on something that is realistic in terms of life cycle of a network or of a station. So again, if I only think about the seismology, because I'm a seismologist, I have the expertise there, some elements are 10 years lifespan, but a seismometer might go 20 or even 30 years. So what we wanted to capture in these 20 years is a full cycle, that all the stations will go at least for a full cycle. So we need to think this of a rolling period. So now we're analyzing these 20 years, but in 2 years could be the following, and then so on and so forth. So this 20-year cycle is a rolling period. So the other thing that we did is, now that we know technically what the network will be needed in the 20 years, let's find out how much it's going to cost us. And for that, we analyze cost of changing or installing the different elements in the last 20 years. Actually, we focus more in the last 10 years because that's when we have good data, good financial data. And with that, we came up with average cost for all the subsystems. And the problem is that if we go and just put numbers here, that means that currently we need a huge amount of money. And then that amount of money will be variable, and there will be some years that we don't need that many, but then again, we need huge amount of money. But also resources, staff resources, in order to actually conduct all the sustainment needs for that peak at the beginning and the first 4 or 6 years. We need lots of money and lots of people to implement the actions. And then we don't need money and we don't need people. What do we do then, right? That's not the way to plan this. So what we did is that we spread the actions over time and smooth the cost. And here you see a smooth graph of costs per biennium. So that would be the amount of money that we need. That would be the level of each bar. And then the color corresponds to the different technology. So for example, the pink one corresponds to infrasound, while the blue one corresponds to primary seismic, right? And then you have these very high peaks. Those very high peaks, green peaks, corresponds to the replacement of an underwater hydroacoustic element. So those elements are super expensive, and they are reflected here. So now, this is what the network needs to be optimally operating, to deliver good data, good quality, and so that the states can benefit from it. So now, let's remember what's the main purpose of the network. The main purpose is to be able to detect any event that happens or that occurs anywhere in the world, no matter if it's underground, underwater, or on the surface, or above the surface. So far, the network has fulfilled its mandate. It has been able to locate the 6 events that have happened in the so far. And we see that depending on the number of stations that were installed at the occurrence of each test, the uncertainty on the location has improved. So we went from an uncertainty area of 800 square kilometers to 100, about 100 square kilometers. So that is very important because we have better clarity on where these tests or these events took place. But detecting events is not the only function, and there's another very important one, and that's discrimination. Discrimination of the event. So last year, in October, the social media went crazy about these two events, claiming that they had been tests conducted by Iran, nuclear tests conducted by Iran. So the IDC collected the data, the analysts looked at it, did all different analyses, and come up with the result that they were actually natural events, that they correspond to the seismicity that happens in the place. So again, the network show its value. It's not only about detecting, but also discriminating. So having all these stations located in the way that they are operating at its most gives you the certainty that they are not tests or that not tests go undetected. Now, having this amazing data with 4 technologies sitting there, only focus on nuclear tests, is a very, very huge investment with little return. It is, as a scientist, you know, that some people's noise is your own data. So you have this amazing set of data that provides you with so much more. And one of them is the possibility of using the network for tsunami early warning. So nowadays, CTBTO has agreements with some countries, with some states, with their tsunami early warning centers to get the data and incorporate it in their pipelines to identify the potential source of an earthquake, better characterize it, and decide on the genesis of the earthquake, if it's tsunamigenic or not. So this is a very good tool and very high value for those countries that face the hazard of tsunamis. But then again, the data is so vast, and there's so much in it that we still don't know. So I only can pick some cool events or cool examples for me to show on how much value we can get as a scientist from this data. One of my favorites is the story of the migration of the whales, the identification of the Pygmalion blue whale. So that's, for me, is an example of I probably would have not considered, because I'm a geophysicist, a seismologist, but then some marine scientists decided that this data could give you that. Of course, the characterization of the Hunga-Tonga Hapai eruption, that it was captured by the 4 technologies. And so people were able to better characterize this very significant eruption. Something that is being used for is also climate change. The temperature of the ocean, we are able to now see the changes from the last decade, because we have data in our hydroacoustic stations. So here is the invitation for you to think of any other possible use for this data. It's open, it's free, it's there. So run the voice, tell other scientists in the world, this is amazing data, and you have the 4 technologies. So just to summarize, the sustainment of the IMS network is key to protect investment. An investment that has lots of returns. An investment that will allow us to continue providing the world with good quality data. A data that allows us to detect events and ensure that no event goes undetected, but also the possibility to discriminate events. This is very important for an organization that is impartial, and it will ensure the states and people in the world that we are able to say this is not a nuclear test. Also, this will allow us to protect this amazing multi-technology network that is not only fulfilling its purpose, but also giving us so much in terms of civil applications on scientific advantage. So again, I encourage you to think on new applications for this amazing set of data. And with that, I thank you for your attention, and I'm open for questions.
Thank you very much. We are a little bit pushed for time, but I see there was maybe I can just mention the online question that we received. And then I would like to encourage maybe everybody, if you do have other questions during the panel session as well, you can please send your questions through as well, and we could then discuss it. So the question here is, as AI-based predictive maintenance tools become increasingly common, to what extent is the IMS network exploring or implementing such approaches to forecast and mitigate potential station outages? Or are we still mostly reliant on reactive procedures when failures occur?
Thank you for the question, and this is a very important one. Currently, we are still reacting, but we want to move forward from there. We don't want to stay there. We desperately need to move from there. So we might not have enough of a manpower to develop the tools to do this proactive analysis and determination of the need of a very near sustainment action. But we have good partners. There are research institutions, national labs, and other people that are developing these tools. So we look forward for those developments. Some were presented during this S&T. There were a couple of presentations on Monday. There were a couple of presentations today. So we want to look to those and look how to implement them, because we really need to move from reactive to proactive. It could be so good if we can foresee the failure of a system, and then we can start planning our actions, start the shipping of the spare parts, or anything that needs to be done, either to wait for the moment that it collapses, or be proactive and change it before it collapses. But at least to reduce the time of failure and between when the failure goes and when the station goes alive. Remember, our objective is to have a very high level of data availability. So for that, we really need to reduce that, and we need IA and all those new tools.
Thank you. So unfortunately, we do need to go into our panel discussion now. So if I could ask if there are any other questions, please feel free to put them on the chat. And then maybe the panel will be able to address them during their discussion. So please let me thank Ch1 for the presentation.